Well, this video is for this handout on Taylor series or power series. And at the bottom of the first page on the handout, well, before I get into that, let me just talk about what this is for, what this is used for. So this is used to approximate or calculate values for the transcendental functions. So transcendental functions are the exponential, y equals e to the x, y equals ln x, and y equals sine or cosine, or really any trigonometric function. So these are called transcendental functions. They're not polynomials. There's no, real nifty way to calculate something like the sine of 73 degrees, okay? And so this is a method that allows us to calculate these values. And in fact, I don't work for Texas Instruments. I don't know how the calculator is programmed, but this is the only way that I know to get these values, okay? And so I assume that this is how the calculator is programmed and how it's generating values. When you want to do e to the third power, it's actually going to use one of these power series to generate an approximate value for e to the third power. Okay, so that's what this is for. Now let's talk about what it is. All right. So at the bottom of the first page on the handout, we have this example. If you remember back in the fall when we were finding tangent lines, let's look at the function I've got here. So this is y equals x cubed minus 5x squared plus 2x plus 3. And it's a graph that looks something like this. And where is this? At the point where x equals 4, we've got this tangent line here, which is y equals 10x minus 45. And of course over here it's not very close to the curve, and that's true over here too. But in this region, right in here, the values for the linear function, 10x minus 45, and the values for the cubic function are actually very close to each other. And then over on the next page, I talk about using this because they match at the point where x is 4 and y is negative 5. That's easy to see here. If you plugged it in here and calculated, you could see that was on that curve as well. Now, if you wanted to find f of 3.95 with our calculator, that wouldn't be too much of too much difficulty. But if you had to do it by hand, it's a heck of a lot easier to plug 3.95 into this and get an approximate value than it is to do all of this calculating. Okay, so that's the general idea for how we approximate values. So this is an example of a linear approximation. So let's look at what goes into doing this, right? So first we find f prime. So we're interested in what's happening at this value, x equals a. So we need to calculate f prime at the point A, right? We need to know the slope of the curve at that point, and then our equation will be y equals f prime at A times x, and then we've got this y-intercept value, right? So at the point where x equals A, y is equal to f of A, if we're working with some generalized function y equals f of x, right? So at the point A, f of A, we can plug that in here. And then B is going to be equal to f of A minus f prime at A, let's see here, times A. All right, so now that's going to make this equation f prime at A times x plus f of A minus f prime at A times A. So let's swap these around here. So that'll be f of A and then f prime of a times x minus f prime of a times a. And so now this is f of a, f prime of a times x minus a. Okay, so there's the general formula for this linear approximation, what we had originally called tangent line. Okay? And it can be useful, you know, to calculate values very close to that x equals a value. All right, so there is the linear approximation. Oh, and we should check it out and make sure that if we call this, let's see here, we can call this P1 of x. That's a first degree polynomial of x. And we want to know, is P1 of a equal to f of a? Okay, well, P1 at a is going to be f of a plus f prime at a. And then we take the a and we plug it in for the x here, and this gives us 0. And so, yeah, P1 of a is equal to f of a. And then we also want the derivative to match up. Okay, so let's see here. P1 of x is f of a, and then f prime at a times x minus a. So let's multiply this out so that it's a little bit easier to take the derivative. Because now if we want p prime, this is a constant. This is just a numerical value. Its derivative is 0. Here's x to the first power, so its derivative will just be f prime at a, whatever that coefficient is there. This is another constant, and its derivative is 0, so there we go. All right, P1 at a is equal to f of a, and P1 prime at a is equal to f prime of a. So that matches up. All right. Now what we're going to do is we're going to make this a better approximation by extending it to a quadratic function. All right. The linear function has its limitations. If we could make a curve, a quadratic curve, then it could approximate another curve like, for instance, if we're doing the sine function, right? So if you've got a linear function cutting through here, it'll be a good approximation for this area in here. But if you want a better approximation, you could use a quadratic, which might do something like this. Okay? And then it would give you a better approximation for more values. All right, so let's make a quadratic approximation now. So, what are we going to do here? All right, so we want P2 of x. We'll start out with the linear piece that we had, and then we'll add on this quadratic term, x minus a squared, and we don't know what this C2 is going to be right now. Okay, so the first thing we want to check, remember that we always want P2 of a to be equal to f of a. We want the first derivative, P2 prime, to be equal to f prime at a. And we want P2 double prime to be equal to f double prime at a as well. All right, so let's see here. P2 at a, this will stay the same. We'll get f prime at a, and then any place we have an x, we'll plug in the a. So these are zeros, and again, we just get, yeah, P2 at a is going to be equal to f of a. All right, so that's good. Now what? P2 prime, all right. Let's see here. We know that when we take the derivative, this is a constant term, so that's going to go to 0. Here, we're going to get f prime at a because that's the coefficient for this x term right here, and then we'll get another 0 there. Over here, we'll get 2c2 times x minus a, and the derivative of what's inside there is 1, so we don't really have to worry about the chain rule. All right, so p2 prime at a will be f prime at a, 2c2, plug in the a for the x, that makes 0. p2 prime at a is f prime at a. Good, that's what we wanted. All right, now we want the second derivative to also match up. So, p2 double prime of x, this is a constant, right? F prime of a, this is going to be a numerical value. When we take its derivative, it'll be 0. Over here we have an x, all right? And so our derivative, when we take that, will be 2c2, and then this 2c2 times a is also a constant. Its derivative is 0. All right, so we want this now, p2 double prime at a, we want that to be f double prime at a, and what we've got is that it's equal to 2 times c2. That means we want to force c2 to be f double prime at a divided by 2. Okay, so our quadratic approximation, p2 of x, should be f of a plus f prime at a times x minus a plus f double prime at a divided by 2 times x minus a squared. So there's the formula for our quadratic approximating polynomial, and if we do that correctly, then all three of these will match up. It'll have the same function value, it'll have the same slope, and this will match the concavities as well. Okay, it'll be concave up or concave down, just like the thing that we're trying to approximate. All right, so that is the quadratic approximating polynomial. Now let's extend it one more time. And let's make this a cubic. All right, so we've got that up to here, and now we're going to put a c3 x minus a cubed, and we want these same things to match up. Oh, and this is going to be a p3 now, because it's a third degree polynomial. All right, so we want p3 at a to be the same as f of a, p3 prime at a to be f prime of a, p3 double prime to be f double prime at a, and then also we want the triple prime at a to be f triple prime at a as well. All right. So again, if we plug in a here, this will be 0, this will be 0, this will be 0, and so p3 at a will just be f of a. Okay, good. Now let's take the first derivative here. p3 prime of x. This is a constant, so it's going to be 0. Here we'll get a derivative of f prime of a. Over here, let's see, these 2's will cancel each other out, and we'll get f double prime of a times x minus a, right? Yeah. And then over here, we'll get 3c3 x minus a squared. And again, the derivative of what's inside there is 1, so we don't really need to worry about the chain rule here, okay? All right. So now, p3 prime at a, anything that has an x minus a is going to become 0. So this will be f prime at a, and then this will be 0, and this will be 0, and there it is. p3 prime at a is f prime of a. Yay. Okay, good. Now what? p3 double prime. So this is a constant right here. Its derivative will be 0. Here, the coefficient of the x will be our derivative, f double prime at a. And then out here, we'll have 3 times 2 C3 x minus a to the first times 1. Okay, so now P3 double prime at A is going to be F double prime at A, and when we plug in the A for the x, that'll be 0, and so now that checks out as well. Okay, that brings us to the third derivative. So P3 triple prime of x, this is a constant, its derivative is 0. Here we'll get the coefficient, 3 times 2c3, and that's it. Okay, now we want this to be equal to F triple prime at A, and the way for that to happen is if C3 is F triple prime over 3 times 2. Okay, so now we're going to stop and generalize. So you can see if we want to continue this for a 4th degree, 5th degree, 6th degree, and so on, that will do the best job of matching up whatever function it is we're trying to approximate. And every time we try to match these derivatives up, as we're taking derivatives, you'll get 3 times 2. And then the next one you'll have 4 times 3 times 2. And then you'll have 5 times 4 times 3 times 2. So the general formula here is C sub n is going to be the nth derivative at the value of A over n factorial. Okay? So now this is the formula for our Taylor series. And the Taylor series says that the approximation P sub n of x will be the sum as k runs from 1 to infinity of the kth derivative at A over k factorial times x minus a to the k power. Okay. And we usually don't go to infinity on these. I'm not sure how far the calculators are programmed to give us 10 decimal place accuracy. But if you go out, to an 8th degree polynomial, I'll try to put, I'll try to show some of those graphs, and you can see how closely they match up. Okay, so there's the general idea for building a Taylor series. Now let's look at some problems here. All right. So in the first set of problems in this handout, the first group of problems, it says, find the quadratic approximating polynomial for the given function centered at a equals 0. So in this formula, we're going to have x minus 0, or just basically x to the k power. And that actually has a particular name. It's called a Maclaurin series. But we'll talk about that on a different handout. And so this would just be x to the k power. All right, so in problem 2, we're working with f of x is equal to the sine of x. And in this set of questions, we're looking for the quadratic approximating polynomial. So let's just write down a general formula for that. F of a, f prime of a times x minus a, and then f double prime over 2 x minus a squared. So we need to know what's f of a, what's f prime of a, what's f double prime of a for a equal to 0. So f prime of the sine is going to be the cosine. F double prime will give us the negative sign. Now let's evaluate these. F of 0, let's see, sine of 0 is 0. Cosine of 0 is 1. And sine of 0 is 0 again. So this one is actually kind of boring because what we get for this P2 of x is equal to 0 plus 1x plus 0 again. And so our fantastic approximating polynomial is just y equals x. And if you look at the picture, remember I was using this a few minutes ago. So there's the sine function, and the line y equals x is actually not a bad approximation for this, for values, you know, in this region right here. Okay? Like I was saying, if you wanted to move out here a little ways, you might want a better approximating polynomial. Okay? We might have to go further out. Okay, so that's problem 2. Let's keep going here. Keep that a equals 0. Problem 4 is, let's see here. This is f of x is equal to 1 plus x to the negative 1/2 power. All right? So we can calculate f of 0 if we want. That's going to be 1, right? Because this is just 1 plus 0 to the negative 1/2. Still going to be 1. All right, our first derivative is negative 1/2, 1 plus x to the negative 1.5. And if we plug in 0, we'll get a 1 here times negative 1/2 equals negative 1/2. And then our second derivative, f double prime, let's see here, that's going to be positive 3/4, 1 plus x to the negative 2.5. So f double prime at 0. Again, this will be 1 here, and we'll just have a positive 3/4 for our coefficient. All right, so now our P2 of x is going to be 1, f of a, and then minus 1/2 x to the first power. Remember, because a is 0, so we don't have to do x minus a. And then plus 3/4 over 2 x squared. Okay, so 1 minus 1/2 x plus this is 3/8 x squared. I'll switch to fractions. They're a little bit easier. All right, now let's take a minute here and take a look at what this graph is actually going to look like. And then what this approximation looks like. All right, so first I'm going to do 1 plus x to the negative 0.5 power. All right, so I'll come over here and show you what it looks like on the calculator rather than trying to get that. I've tried that screen with this camera, it just doesn't seem to work. I found that this is what works best. So we got to get the camera to focus first. There we go. So there's what we want to graph, 1 plus x to the negative 0.5 power. And then let's see what that looks like in our standard window here. Okay, there it is. Now, let's go in and put in our approximation. 1 minus 0.5x plus 0.375, which is 3/8. All right. Okay. 0.375 x squared. X squared. So, there's what we're going to graph alongside the original function. And there it is. And you can see right around 0 they match up pretty nicely. In fact, I'll do a zoom box and kind of zoom in on just that region right there. And then we'll get a better look at what they look like. So there's that zoom in. There's the function again. And then here comes the approximation. And you can see how they line up really nicely right around 0. Okay? And if we wanted to have that extend further out, then we would need cubic pieces or 4th degree or 5th degree pieces. Okay? All right. So that's problem 4. Let's look at the next one here. All right. Where are we? Okay. So, problem 6, 1 plus x to the negative 2 power. All right, so our derivative f prime is negative 2, 1 plus x to the negative 3. f double prime positive 6, 1 plus x to the negative 4. So f of 0 is going to be 1, f prime of 0 is going to be negative 2, f double prime of 0 will be 6. And then our p2 of x will be 1 minus 2x plus 6 over 2 x squared. Don't forget this divided by 2 here. So 1 minus 2x plus 3x squared. All right, now let's take a look at that one as well. Okay, so 1 minus x to the negative 2 power, and then 1 minus 2x plus 3x squared. Okay, let's get it to focus again. So there's our two functions. And now let's go look in the standard window and see what it looks like when we graph them. There's the original function. And then here comes the approximation. And you can see again, it lines up pretty nicely. I'll do a zoom box around that region around the origin. And then you can see how nicely they line up right around where x equals 0. And there it is. Okay. That's problem 6. Let's see here. Problem 8 is just 1 plus x to the positive 1/2 power. Let's see here. Let's see. Problem 8, our function now is 1 plus x to the 1/2. So that derivative will be a half 1 plus x to the negative 1/2, and this will be negative 1/4 x to the negative 3/2. So with our x value of 0, again, this will be 1, this will be a half, and this will be negative 1/4. So this will be 1 plus a half x minus a fourth divided by 2, so that's an eighth x squared. Okay, so let's look at these two functions. So, let's see here, square root 1 plus x, and then 1 plus a half x minus an eighth x squared. Okay. So, let's see what these look like. So there's the square root 1 plus x, and then our quadratic approximating polynomial. And let's see what they look like on the graph. So there's the original function. Here comes the approximating polynomial. And I won't zoom in on this one. You can see it matches up really nicely. Okay. So those are some good problems to get us started on building these approximating polynomials. And then the last couple problems in this problem set have to do with using the polynomial to actually make an approximation. So let's look at problem 10 here. Problem 10, we want to approximate 1 over the square root of 1.08 if we consider f of x to be 1 over the square root of 1 plus x. And pulling this off makes this x value very small, okay? And remember how the approximations were better right around where x was 0, so we're not going to be too far from 0 if x is 0.08. All right, then we're going to use this approximating polynomial, p2 of x, 1 plus a half x minus an eighth x squared. And we want to do this for x equal to 0.08. So we'll get the calculator out here, and we'll do 1 plus a half times 0.08 minus an eighth times 0.08 squared. So let's see what we get here. A half times 0.08 and then minus 1/8 times 0.08 squared. And let's see here. Is that correct? I thought I got a different, yeah, I got a different answer last time. Problem 10. Oh, I was looking at the, I wrote down the approximating polynomial for problem 9. All right. Well, I'm not going to erase the whole video just because of that. So let's just correct it. All right. So the approximating polynomial for problem 10 is 1 minus a half x plus 3/8 x squared. All right. So 1 minus a half times 0.08 plus 3/8 times 0.08 squared. And you can kind of see that the linear approximating polynomial is right there. It's just 1 minus 0.04, which is about 0.96. Okay? But let's calculate the quadratic approximation. And let's see here. 1 minus a half times 0.8 plus 3/8 times 0.08 squared. And there we go. So this one's going to be 0.9624. So you can see it's a little bit bigger than our linear approximation. And what actually is f of 0.08? What is 1 divided by the square root of 1.08 approximately? So this is going to be 0.96225 or so. And so you can see we're pretty close here, right? We're off by like 2 10,000ths, right? And so how good the approximation needs to be depends on what you're using it for. All right, let's look at one more, and then we'll wrap things up for this assignment. Problem 12. Let's see here. We want to calculate e to the minus 0.15 power. And we're going to use f of x is equal to e to the minus x. So the minus is already in the formula. Our x value in this is just going to be 0.15. And our p2 of x here is what? 1 minus x plus x squared over 2. Right. Okay. So p2 of positive 0.15, remember because that negative is part of the formula, is going to be 1 minus 0.15 plus 0.15 squared divided by 2. So let's see here, 1 minus 0.15. So just right there, you can see the linear approximation is going to be about 0.85. We'll see how close that actually is. Plus 0.15 squared divided by 2. And so that's 0.86125. And then what actually is the calculation for e to the negative 0.15 power? Is about 0.8607079. So you can see we're off in what, the thousandths place? We're off by about 5 10,000ths here from 7 to 12. And that's not so bad. Okay? All right. So I think that's a good introduction to this topic. We'll finish working our way through this handout. There are a couple more problems towards the end here, but I'll save those for another video. Thanks.